Hi and welcome back. Today I wanted to talk to you about quantization of energy in string theory. And the video will be the first part of the series where I'll explain particularly how the energy works with string theory. So, let's start it then. First things first, what is a energy in quantum mechanics, for instance? It's named Hamiltonian, and Hamiltonian is nothing but the representation of E kinetic plus E potential. This is it. The sum of kinetic energy and potential energy is a Hamiltonian. Now let's think. In case we have a string, better to say, what is the energy will be dependent on? What will the energy will be dependent on? Well, it depends highly on how it moves, kind of how it oscillates back and forth, all of those actions. Imagine a string going in this way. So you just count in which direction it moves and you are able to find out its energy. So here we are making it. It will be our kinetic energy. It's here. What we do first? It's a standard formula of kinetic energy, mv squared over 2. Then you modify it to the derivative form, m dot x squared over 2. And after it, you make a trick here. And let's notice that this is a mu, not m. What we did here, look, at this part we split the string into tiny pieces, a lot of them. A lot of means an enormous number, uncountable. The number goes to infinity. So there is a lot of them, so you're not able to count them. And the mass of each mu will equal to the mass of a whole string over n, the number of them. It will be your mu. And you're kind of thinking how those particles, tiny things better to say, will move. This gives you the whole kinetic energy. I'll tell why the model is better later, because it will really simplify our work. What we do on the next stage is actually the E potential. Let's think. What will be the E potential? Look, between those particles, they are in some way connected. Kind of, in case they are separated from one another and they are not connected, they'll simply go away and escape the space. So they are in some way connected, and those kind of things are going to be springs. And kind of, in case you remember the potential energy of a spring, it's this formula. Kind of, it's spring constant times the square of the distance that you are kind of trying to expand on. So it's going to be your dx. And in case we think of a huge number of those kind of particles and those springs, it's gonna be effective to write it in this form. Kind of, from the every nth particle goes a spring to another one, to another particle, x and minus 1. And kind of, those are coordinates, and because of the coordinates, you may find out the dx. So it's a whole formula. Oh, sorry, I forgot to put here square. Yeah. So uh, it was all about the number of the tiny particles, the constituents of a spring. And what if we try to get rid of them? Because of, well, they go to infinity. And it's not a good sign because everything that goes to infinity just blows the mind of physicists. So let's try to remove them. What if the number of particles that we have in a spring will be placed on a certain interval of sigma. Yeah, let it be sigma, which goes from 0 to pi. Why from 0 to pi? Because some springs, as you know, they may be circles. And kind of it's gonna be going from 0 to 2 pi. So we just try to use the standard deviation standards and put here pi. So we kind of make it uniform, the spring at this time. We get rid of the infinity and we establish the parameter of sigma. What we do next? As I stated, we take the mu of each of those kind of particles as 1 over n, or mass over n, and we define mass in mass units. It will be 1, so 1 unit for one string. What we do next is actually the establishing of the k, the spring constant. It will be n over pi squared. So don't think of this, let's think of why it's n. Well, what 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 actually goes on here is that in case you have a lot of tiny particles and springs attached to them, uh, kind of those are particles. Uh, in case you connect them directly in this way and try to stretch the whole construction, it will get really easy. You may try it at your home, just find two springs, connect them to each other in this way, and you'll find out that it's even easier than stretching each of those separately. So it's because of this kind of rule of the string summation, so something of this. So because of there is a lot of them, kind of because of the power you need to stretch the thing in this way is gonna fall down as f over n cos of n. So to normalize it and to make it harder to stretch, not to make everything easier. So you see, the physicists don't like to make easy things. They wanna kind of be outstanding. So we'll multiply it times n, and n will cancel, and we'll be left with our usual f, the power. So force. This is what for we use the n. And the delta sigma, we'll define it as pi over n. Sorry. To say it fairly, just an interval over the number of particles. So we define all of the constants. Now let's apply them. First, let's insert our m into the kinetic mass, kinetic energy. Look, we have 1 over 2, so it's this equation, this. And instead of mu, we'll use this notation. We put, instead of mu, 1 over n times x squared. what we do next, we just rewrite it and multiply times pi and divide over pi. We get this thing. And look, doesn't it resemble use anything? Well, it's the sigma. It's here. So we'll actually modify it and it will be x dot squared over pi times the sigma. And of course over 2, 1 over 2 at the start. And when you kind of have a sum or over a small part of interval, small interval, you may actually use the Newton's law and turn it into an integral. So kind of it will be an integral going from 0 to pi. We define that the sigma goes from 0 to pi. And the 2 pi factor, you may just take it from the whole equation at the starting point. And everything else will be left the same. So you got your kinetic energy. And it's really useful to have an equation of this kind because you just know the function of x on a certain interval, and here you are able to count anything that you want. Isn't it great? So the following is the potential energy. Potential energy was this, as you remember, k times delta x squared over 2. So what we have here, we change the k constant on the n over pi squared. So it's so now it is 1 over 2 the sum from n equals to 0 to infinity, n over pi squared times delta x squared. So you just rewrite it, the first part, so the sum and the 1 over 2 factor, and then the magic happens. Look, we know that pi over n is d theta, yeah? And what if we turn it in the other order? Kind of, it's gonna be n over pi. See? So we just made it. It's gonna be n over pi equals 1 over d theta. So kind of you have 1 over pi times d theta. That's what we did. We rewrite delta x squared and move on. It's 1 over 2 sum and 1 over pi, so it's still here. And what I did next is kind of I multiply times d theta and divide. See, there is one more d theta. There was only one d theta here. Now there are two of those. Kind of you multiply and divide, and you're able to do it. What happens again? You have the d theta and sum. It turns into integral from pi to from 0 to pi, and the left will be the delta x over d theta squared, and this will be really useful. You'll know, I'll tell you why later, but you'll definitely appreciate it. So, and you got the potential energy, and it's again neat form comparing to what we had here, so hard to find, and here n goes to infinity, uncomfortable to work with. And here it's just from 0 to pi, and you know what you are counting, and all of those things. So really useful. So as a whole, the Hamiltonian will equal to the 1 over 2 pi going from 0 to pi times this, look, this part is actually the kinetic energy. What's left? So kind of in the parentheses, and this is our potential energy. So you sum them up and integrate over d sigma. This is it. You have your Hamiltonian, and in terms of Lagrangian, it will be 1 over 2 pi p from 0 to pi x dot squared minus dx over d theta d sigma squared. Yeah, yeah. So don't forget, this is a potential. This is our potential energy, and this is kinetic energy. So I think that's all for today. In the next part, we'll talk about how, in particular, we are able to quantize those things, to know how many n's are here. So kind of we'll apply QM to our string theory. So in the end, don't forget to subscribe, not to miss the next video. And of course, please like the video. I really appreciate it. Please, 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 please. Thank you. So, have a great time and see ya. Bye.